Section 5.1 is areas and distances. This begins our consideration of the integral calculus. So the first thing we need to understand is what the sort of essential problem is here, and that's finding the area underneath a curve. And if we look down below, we'll get into the example in just a moment. We'll see that, if we have a curve y equals x squared, and we want to know the area beneath the curve or between it and the x-axis, this is a non-trivial problem, right? What we see we're doing here in this example, as far as the work that's been done, is we're approximating it with rectangles. We see that there's an error, some amount of error in those approximations. Those are all the areas that we miss, where the rectangle doesn't cover the area underneath the curve. So we'll see how this evolves and how we can make this approximation more accurate, and also how to make it exactly the value that's underneath the curve. And that's one of the impressive things that integral calculus can do for us. And though that does seem like a really trivial thing to know about the area beneath the curve, it really turns out to be a lot of very important calculations, or that area underneath the curve tends to represent a lot of very important calculations throughout the sciences and applications of mathematics. So just to jump right in, we're going to do a straightforward example without any real introduction of how to go about doing this. We're going to use the most intuitive process we could imagine and approximate the area underneath the curve y equals x squared. So this is use rectangles with left endpoints on the curve to approximate the area under the parabola from 0 to 1. I say the parabola, so written in that's y equals x squared to be more specific about that. We're going from 0 to 1, x values from 0 to 1. And what we want to know is what the area underneath this curve is, the area between the curve and the x-axis. So in order to approximate this with left endpoints, we need to select endpoints for these rectangles that make up the left side of the rectangle, right? So what we'll do, since it's easy to calculate the area of a rectangle, it's just the width. So the width is delta x for each of these rectangles. We're going to split the interval into n equally length intervals, and we're going to multiply by the height of each rectangle times its width in order to find the area of the rectangle. What's the height of one of these rectangles? Well, notice that that point is on the function, and the height is f of whatever this x value is down here. So that's what will generate all of that. So our first task is to determine delta x. What width should our rectangles be? Now, they don't tell us how many points to use, so we'll just choose an arbitrary amount. We're going from 0 to 1, so let's split it up into 4 rectangles. Typically, a problem will say, use rectangles with left endpoints, or use 4 rectangles, or use 8 rectangles with left endpoints to approximate the area under a given curve between 2 points. So in our case, we have 4. We've chosen to use 4. We need to split our interval up into 4 equally length subintervals. So this is b minus a, 1 minus 0, over n. We've chosen n to be 4. We want 4 subintervals. So that length comes out to 1/4. So each of these 4 widths for each of these rectangles is 1/4 now. So that's a big part of the work, the calculation, really. The next is we realize that the area under the curve, the exact area, that's, has a curvy side to it, is approximated by the area contained in each of the 4 rectangles. Now, the first rectangle is flat. It has area 0 in it, right? We're using left endpoints. There's an option to use right endpoints, but we are instructed to use left in this case. So it's all 4 of the rectangle's areas listed as R1 through R4 added together. It's as simple as that. So what we'll do is take, it's the area of the first rectangle, which is this flat one here, and there actually isn't any area, so it's 0, right? It's got height 0, so 0 times delta x is 0. And it'll be delta x times the height of the second rectangle, delta x times the height of the third rectangle, and so on to the fourth. And, well, what are these heights? Again, the heights are the function values, right? So what we need to know is what the value of the function is at each of these points. Well, more than knowing what the value of the function is at each of those points, we need to know what the points are. And they're listed above, but let's see how we got those, right? So we know that our left endpoint was 0, our leftmost, and then we're going to step 1/4 a delta x step to the right, and that's going to be 1/4. Then we're going to step another 1/4, another delta x step to the right. So we'll add 1/4 to 1/4 to get 1/2. We'll add 1/4 to 1/2 to get 3/4. Add 1/4 to 3/4 to get 1. Okay. When we finish this process, if we just do this stepped adding procedure like we just did here, we should always start with our initial left endpoint and end with our right endpoint. If that doesn't work out, if we skip over the right endpoint, then something's gone wrong. So that's a nice check. Okay, there are formulas for delta x in these intermediate endpoints, but for now, this is just an easy way to step it out. You'll definitely want to learn how to use the formulas for other problems because it makes this a lot quicker and a lot more reliable. Okay, so each of these heights, so now we know our points, right? We know we're going to go from 0 to 1/4 to 1/2 to 3/4, right? These are these 4 left endpoints respectively. We don't use 1 because there's no rectangle on the right side of it. 1 does not give us the left endpoint of a rectangle that's underneath this curve. So 1 is cut out. So that one's not in there. Where we're using right endpoints, we would use 1. Maybe that's for another example. Now, f of each of these values will be f of 0, f of 1/4, f of 1/2, and f of 3/4. So let's see where that comes in. It's this line here. Well, f of 0 is just 0 squared. So we zeroed that out nice and early. And, well, what's delta x? Remember we calculated delta x, it was 1/4. Every one of these terms has a delta x multiple in it, so we just factor delta x out to the front here. And then we're going to do f of 1/4, f of 1/2, and f of 3/4. Well, f of x is the function x squared. Remember that from the beginning. Here. And, well, we square each of these, add these numbers up, and what we have is that our rectangular area, or the area of all the rectangles together, comes out to 7/32, and that gives us an approximation of the actual area that's underneath the curve y equals f of x. Now, some things are obvious. One of those being that our estimation here, our approximation, is an underestimate, right? It misses some of these spaces that it doesn't fill in rectangular area with. If we did a right endpoint approximation, we would have the opposite effect. We would have rectangles that look like this. Oh, one of those is not right at all. Here's this one. And that. These would be right endpoint approximations. We would use this point and not this point, because those are right endpoints of our 4 rectangles, and we'd see that we would overestimate the area with right endpoints. The other way to make this more accurate, though, would be rather than to use right versus left, we would just split the subinterval into more, or split the interval into smaller subintervals. Maybe we use 8 rectangles, and that might look something like this. And we see when we do that, we start to fill in more of the distance, right? So that fills in this portion, this portion, this portion, and this that was missing before. So we do a better job of approximating. If we use 16 or 20 or 100 rectangles, then we do an even better job. So behind all of this, we'll notice that there's a limiting process. So we'll want to take the limit as the width of the rectangles goes to 0, but also as the number of rectangles goes to infinity. We'll see how that's handled in just a moment. That's going to be through a nice limit definition. Okay, so right endpoints. This is the same thing I just drew earlier, right? Same function, y equals x squared from 0 to 1. And our rectangles in this case are the ones that I sketched over the last picture. We still have the same subinterval endpoints. Now we don't use 0 because 0 is not a right endpoint for a rectangle. We use 0, 1/4, or so we use 1/4, 1/2, 3/4, and 1. Those are right endpoints for these rectangles. Notice these rectangles altogether overestimate the area in the curve because we have portions of the rectangles that are above the curve. So once we put all that together in the same formula, it's the area of all four of those rectangles, delta x, the width, times the height, f of 1/4. That's the area of the leftmost rectangle, and so on down the line for the other three. We add all of those up after we take factor 1/4 or delta x away from all four of these terms. We add f of 1/4, f of 1/2, f of 3/4, and f of 1. Those are all just those numbers squared because f of x equals x squared. And when we're done simplifying all of this, we get 15 over 32. And it's worth noting that our previous problem, our previous approximation, was 7 over 32. So we indeed did approximate less area with the left endpoint approximations than we did with the right endpoint approximation. And we used the same number of rectangles. So obviously the two methods work out to different values, provided we only use a finite number of rectangles. Okay, we can do a little bit better than this. And this is jumping ahead just a touch, but clearly we can use a limiting process to calculate the area underneath this curve. If we take infinitely many rectangles underneath this curve with infinitesimal, that's essentially think of that as infinitely small widths or near zero widths, then what we can do is eventually approach a point where our rectangles accumulate all the area underneath the curve and no excess, and they don't miss any of the area underneath it, and we get the value exactly. So let's see how we might go about doing that. Okay, we're given this really nice formula right here. This is a number from result from number theory, which is somewhat easy to prove. It can be proven inductively, but we just know that it happens to work, and it's a formula that's going to be very useful for us in this situation. Now let's read this notation. It might be the first time we've seen summation notation here, so let's have a look at that. The sum of the first n integers, k equals 1 through n, squared is equal to this value. That's interesting. What is this summation telling us, though? This summation is equal to 1 squared. I start at my initial index value, k equals 1. I square it, and then I add to it the next value. I increment up by 1 and go to 2 squared plus, and then 3 squared plus, and then I'll count this all the way up until I get to n minus 1 squared plus n. Oh, these are not n's. These should be k's. No, these are n's. That's right. Up to n squared. And I stop at my upper index. This is my stopping index. Right? And it's inclusive. I'll use it. Same as k equals 1. I start there and I stop here. And I increment by natural numbers. We'll always use our index as natural numbers here. So it turns out that if we sum up the first n integers, so if n were to be equal to 3, then I would just have written this down. If n is 3, the sum of the first three integers is 1 plus 4 plus 9. We'll see that that's 14. Well, if I plug 3 into this formula, what do I get? 3 times 4 is 12, times 6 plus 1 is 7, so 12 times 7 is 84. Divide by 6, 84 divided by 6 is 42 divided by 3, and 42 divided by 3 is 14. So you see that this formula actually does work. So just an interesting sort of diversion, but it's going to be very useful for our purposes here in a moment. Okay, so let's get back to the area question, and we're talking about the area from 0 to 1 underneath the curve y equals x squared. And this formula is going to turn out to help us out of a tight spot here in the work below. So delta x, let's calculate delta x, the area under y equals x squared on the interval 0 to 1. Delta x is always calculated by this formula. It's b minus a divided by n, where n is the number of rectangles we'd like to use to calculate the area under the curve, or to approximate it. So 1 minus 0 over n is 1 over n. So that's delta x now. That will be part of our formula in a moment. We can go about setting up all of our subinterval endpoints as follows. X naught or x0 is the first or leftmost endpoint every time. That will always be the case. Now, whether or not it's 0, it may or may not be 0, but it's the left endpoint. X naught is the left endpoint every time. Okay, then x1. x1 is equal to 0 plus we step to the right by a value of delta x, right? For x2, we add another delta x. So we step from 0 to delta x steps. And if we move on with that, x sub k in general is the left endpoint plus k over n, or k times delta x, right? That'll be our formula generally, and we'll see that on the next page. But in our case, we see that, well, for each of these, delta x is 1 over n, so this was just 1 over n. This was just 2 over n, and so on. X sub k is k over n. So for any k value, arbitrary or otherwise, I can plug this in to my formula here to talk about what, so x1, x2, all the way up to xk, and then all the way up to xn, our ending value. I can write down what these things are. This is going to be the value for the x sub k case, k over n. Okay, so that's a useful thing, because what I need to do is I need to take the function and evaluate it at that x value. Okay, now to get the area exactly, I use the limit as n approaches infinity in order to take infinitely many rectangles. I'm going to add up infinitely many rectangles through this summation that we have right here. It's a pretty powerful bit of notation. We'll see how to handle it in just a moment. Now remember, I've got delta x times each of these rectangle heights, so that way I actually calculate the rectangle area. And if I do this process, right, letting the limit, taking the limit as n goes to infinity, what will happen to delta x? Well, delta x is 1 over n, so its length shrinks to 0 in this limit. And for the f of x's, f of xi's, well, we get infinitely many of them. So that seems somewhat problematic, but thanks to this formula, we'll see a nice way out of this. And it's a bit of it's some clever trickery, but it's completely valid. And we'll work on problems like this a little bit later in this chapter, but for now it's nice to see it all work out exactly, at least once, and then we'll come back around to it later. So I'm going to write this sum in summation notation. So I've just repacked this into sigma notation, right? So what does this sigma notation tell me? We'll ignore the limit for now. Just look here. It says start at k equals 1. And we're going to have delta x times f of x1. And then we're going to have k equals 2. Delta x times f of x2. Notice that both of those terms are in this sum, and it goes onward until we get to delta x times f of x sub n, and that's where we stop. It's this point here. Okay, outside of all that, we know that we want this limit to happen. So that's the last thing we'll settle in this problem, is the limit. We'll work our way from the inside to the outside. So moving on from that, we know that delta x is 1 over n, so we fill that in. We know that x sub k, we calculated that off to the right, down there at the bottom left, is k over n. So this is f of k over n. Well, what does the function f do? It takes its argument and it squares it, right? F of x is equal to x squared. Forget that. Now, we know how to apply this function to k over n. So our sum end, the term in the summation, is now 1 over n, that's our delta x that was already there, times k over n squared. That's just applying the function f to k over n. Okay, well, this will be k squared over n squared. And I have a 1 over n here, so this is going to end up being n cubed with a k squared in the numerator. And that's exactly what the next line looks like. K squared over n cubed. Everything else remains the same. Like I said, we don't worry about the limit. We just keep writing it. We take it along with us. We'll evaluate it when we're done. 1 over n cubed. Well, pause for a moment and realize this. The running variable here, our index variable, is k. N is just fixed. Well, n is fixed until we take the limit. But the summation just knows that n is where it stops. N is not a number that the summation changes. So n is a constant with respect to the summation. So n or n cubed can come out as a factor times the sum, right? And that looks like this. And now all we're dealing with is the sum from k equals 1 to n of k squared inside this summation. And this is a point where we can look back and say, oh, we have a formula for that. That thing is equal to n times n plus 1 over, or times 2n plus 1 over 6. Okay, and that's what we'll do. We'll write that in here. This term is swapped out entirely. The summation goes away, and we replace it with this expression. It's because these two highlighted pieces are equal to each other. That's the formula that was given to us in this problem. And this is the key step, because at this point, the only work left to do is to evaluate the limit as n goes to infinity of this expression right here. And that's pretty easy to do because it's just a rational function when we're done multiplying all these terms together. So what we see is we have n times n plus 1 became n squared plus n times 2n plus 1, right? I'm just starting to simplify my numerator. And that's over 6n cubed, right? I have a factor of n cubed in the denominator I needed to multiply through there. So we've done that. And we're going to keep moving on this. Let's multiply these two binomials times each other. Get this this term here. We have 2n cubed is our leading term over 6n cubed. And it really turns out it looks like I was just a little bit short here. I didn't bother to fill in the difference or the terms in the middle because it really doesn't matter. No term has got a larger degree than n cubed in my numerator. So this is already my lead term. I don't really need all the middle terms and the end terms. So now I just look at the lead term over the function in the denominator. Now, of course, if you want to be more careful and be sure about it, fill those in. It's probably appropriate to do so generally, but this is just quick work here. It looks like as n goes to infinity, since the degrees of these polynomials match in the numerator and the denominator, cubed and cubed, my limit is going to be a ratio of the coefficients, and that's 2 over 6, and that's equal to 1/3. So that is the exact area that's underneath the curve y equals x squared from 0 to 1. And that was done through a limiting process. Now, we didn't do this graphically. We didn't see it happen graphically. But in fact, what the limit did for us with this summation was it allowed us to take the sum of a bunch of rectangles and let that number of rectangles climb up to infinity while their widths shrunk down to an infinitesimal or nearly zero amount, which is a pretty impressive feat. Now, compare our answer of 1/3 to our approximations. 1/3 here, 15 over 32. That's a little bit bigger than, that's close to 11 over 33, which is about a third, right? It's reasonable. But it's an overestimate, right? It's too big. Whereas on this page, 7 over 32, I guess it's kind of close to 11 over 33. Maybe what's another one we could try? 30. It's close to 6 over 10 over 30. Not really, but it's within the ballpark, right? So our approximation seems somewhat close. Had we done n equals 8 approximations here, what we would find is that this number would grow closer to 1/3, right? Or if we did 16 and so on. In other words, take a limiting process of more and more rectangles with narrower widths, right? And we'll get the exact area of that's underneath the curve. So there we have it. That's our first introduction to this thing. So that's the sort of organic process that floats around. This is a trick. There are two more tricks like it, and that's in the textbook, and we'll work on those a little bit later. But for now, let's meet the main operating definition for this section. And that's this definition. The area of the region S that lies under the graph of the continuous function f, so notice the function must be continuous, and in the interval a to b is the limit of the sum of the areas of approximating rectangles. Limit of the sum of the areas of approximating rectangles. So the limit as n approaches infinity of right endpoints in the sub n being right endpoints with n of them. So this is f of x1 times delta x, so that's the area of the first rectangle, plus f of x2 times delta x, all the way up to f of xn times delta x, right? Our n rectangles in this case, if we're taking n to go to infinity, then we're, of course, finding the exact area that's in there. All the while, delta x is shrinking while x goes to infinity. That should be a plus there. We're adding all of those areas together. And remember that this is written here, exactly, right? The summation means the exact same thing that we're reading up here. So it's nice to write this as the limit of the sum of these terms. Okay, we're also provided with a convenient definition for delta x. Delta x is always b minus a over n, right? This is our interval, a to b. We'll divide it into n subintervals, and there we'll have it. Okay, so let's have a look at another example. What they ask us to do here is they say use the definition, and be careful about what they ask you to do with some of these problems, to find an expression for the area under the graph of f as a limit. Do not evaluate the limit. Okay, so what they're telling us to do is set this up, or even better, set this up. They don't say use sigma notation, so we have an out. We don't have to write it in this more complicated notation here, or I guess this more simplified notation, which requires a challenging step from here to there. But so I'll do both. But since we're not constrained to write it with sigma notation or not, then we could just stop when we get to the upper notation. Okay, so here's our function. F of x is this rational function, 2x over x squared plus 1, and we're on the interval from 1 to 3. So a to b, or a is 1 and b is 3. So we're going to use right endpoints. It doesn't really matter if we use right or left endpoints. We just chose to use right endpoints here and gave our definition that way. Left endpoints would bring us to the same situation. So we'll just stick with right endpoints. And to calculate our right endpoints, what we need to know is delta x. Well, delta x is b minus a over n. In this case, we're going from 1 to 3. So this is 3 minus 1 over n. So delta x is 2 over n. This is what it is, right? That n should be there because n is going to change, right? N changes in the limit as n goes to infinity. All right. Now, x1 is a plus k times delta x. Well, k is the index, or xk is a plus k times delta x. Okay. In the case of 1, well, there's 1 times delta x. So we move 1 delta x length to the right of a. We have 1 plus 2 over n. For x2, it's a, or 1, plus 2, matching the subscript, times delta x. Delta x is 2 over n. And when we add all this up, we've got 1 plus 4 over n when we multiply that out. Same thing for 3, 1 plus 6 over n. This is 3 deltas to the right of 1, or to the right of a. Now for our kth x value, or x sub k, it's 1, the value a. So notice that this is the same all the way through, plus k, matching the subscript, times delta x, 2 over n. So this is our general expression for x sub k, and that's important because we probably want to use that at some point. Now x sub n, when we get all the way to the end, is n, right? Subscripts match here times delta x added to our 1. And what we have in this case is 1 plus, well, n times 2 over n is 2, and then 1 plus 2, and 1 plus 2 is 3. Okay, so it's nice to check. We begin with our leftmost endpoint. Let's see, well, x naught, sorry, we don't use x naught because it's not a right endpoint. We use x1 because it's our first right endpoint, and we end at our last right endpoint, which is the right endpoint of the given interval. Okay, let's take all of this information and use it in to complete the objective here, right? They ask us to find an expression for the area under the curve as a limit, but do not evaluate that limit. So we don't have to do the work of evaluating this limit. So our answer will include that limit in it. So in general, remember that our area A is the limit as n approaches infinity of, well, width times height of rectangle plus all the way through to the width times the height of the nth rectangle. So to fill in the details, delta x is 2 over n, right? So it fills in all these places. x1 is 1 plus 2 over n. You can look off to the right to see that. xn is 3, and everybody in between, well, fits one of those values, right? So for now, we're just writing it out. We don't know how many in between here, but so that the ellipses take care of that or fill in for that. And so what we can write ultimately is that, well, our area is the limit as n approaches infinity of this 2 over n delta x times what does the function do? It's 2 times x, times 1 plus 2 over n over 1 plus 2 over n squared plus 1. All right, what was all that about? Remember to look up here. How was our function defined? 2 times whatever you plug into f. So 1 plus 2 over n, that's our numerator. And that is 2 times this x value here. And then over that x value squared plus 1. Right, so there's that x value squared plus 1. So that makes up our denominator. And we'll do that for all of the n terms down the line. Here's our nth term here. Oh, sorry, this is our kth term, right? So for any one in between, this is f of xk. Remember that xk was this value. That's good to know. Sort of our general term is what we'll call that. So here's 2 times xk over xk squared plus 1. 2xk over xk squared plus 1. Right? That's us executing the formula on the variable xk, knowing that xk is equal to 1 plus 2k over n, and so on up to the nth value, right? So there we have it, right? This is a nice way. We could write our nth one in here, which would just be f of 3, so 2 times, 3 over 3 squared plus 1, but we don't really need to do that. Or maybe it's a nice thing for completion's sake, but the best way to write one of these is really with sigma notation, and most of the time we'll prefer to do that anyway. The good news is this: in order to write this with sigma notation, we just have to realize where we start. We start at x1. This is the case when k is 1. Notice our general term gives us exactly this when k is equal to 1. So that's the term that sets the recipe for the sigma notation. So we just use 2 over n, it's delta x, it's this part right here, right, delta x, and then times our f of x sub k term. Well, we've already written down f of x sub k, and there it is. And this term, written in here in this series notation, or this sigma notation, is, well, that's going to generate our area exactly, right? So we take the limit as n approaches infinity of this sum. So this will make the sum grow to infinitely many terms. The delta x's will be shrinking in their widths, and this will converge. Well, if it does converge to some finite number, then we know that the area underneath that curve is exactly whatever that finite number is. Now we don't have to work this one out. This one's a bit complicated, a little tricky. So this is one type of conceptual problem we'll have, is just set it up, express the area under the curve as a limit, and leave it alone from there, right? That's all you have to do. So ultimately, our task will be to evaluate the area underneath the curve, but we're going to have better methods as we move through this chapter. So one last thing to look at in 5.1 is the notion of distance. So whereas we were just computing area, if we sort of change our mindset, that was in an abstract situation, some function y equals f of x, we wanted to know the area underneath the curve. Well, if we're given a velocity function and we graph it with respect to time, so the velocity of something with respect to some time, this being v of t, right? Well, if we think about what the area of velocity of one of these rectangles is, we get a really nice practical interpretation of this. So suppose we just knew, call this the velocity profile of a given object or particle, right? We just happen to know for every 5 seconds what its velocity was, right? Or maybe it was even, a nice function v of t, but anyway, if we take the velocity, the height of one of these rectangles, and multiply it by the time, so velocity times time, the area of one of these rectangles actually represents the distance that this object travels in that interval. So again, that's because time, the width, times the velocity, the height, that's velocity times time. Well, velocity times time is distance. So each of these rectangles' areas is a distance here. So that's really a nice connection to make. And this isn't the only type of application for these, but it's one of the most intuitive and general ones to come up with. So what is this the velocity of? It's the velocity of a car accelerating from rest to a speed of 70 miles per hour in 5-second increments. It's given by this table right here. Okay, they ask us to estimate the distance traveled during this period. So this is a common form of these problems as well. So we don't have a continuous function v with respect to time, but we do have 5-second increments, right? So we can probably do a reasonable job of approximating how far this car has traveled based on these 5-second measurements of the velocity. Now these are instantaneous, or we can interpret these to be instantaneous measurements. Maybe we looked at the speedometer at the 5-second mark, at the 10-second mark, at the 15, so on, and recorded those on the table. So well, let's get at it, right? Let's see what these distances are. So the distance here is the change in time, each increment, times the velocity of each of these moments, right? So the left endpoint approximation looks like this. I start at the left endpoint of my interval, time t equals 0, and that's the endpoint of a rectangle. Well, at time t equals 0, the rectangle has height 0, the velocity was 0, so that's a flat line until we get to 5. Well, at time t equals 5, the rectangle has height 30. That's marked off right here. And that's a flat constant 30 that we assume. We just assume it traveled 30 miles per hour until we get to time t equals 10. Of course, it traveled differently. It probably followed some profile like this curve here suggests. We don't have that, so we can only approximate the best, using either the left or right endpoint approximation. Okay, so here we are, and as we progress through this, we stop at time t equals 30. So if we want to know what our distance is, we notice that each of these increments is 5-second increments. So that's good. So each of them is times delta t. So our distance is delta t times each of our 6 velocities that we have here. 6 of those endpoints altogether. And Well, I factored out the delta t because we can. So that's 5 times, and then I just write down 0 through 68.5 as a sum. I add all of those up, I multiply them by 5, the delta x or delta t out there, and I get that the distance traveled is approximately 1,382.5. Did they give us a unit? No, they don't. So maybe that's feet, right? We really don't know, right? So we want to be careful about what the units are because, for instance, if this was in miles per hour and these are in seconds, we need to translate this because what we have here is seconds times miles per hour. And those two things don't just cancel to give us miles. They cancel to give us something different. We'd have to convert the time. But just to keep this example clean, we've just seem to have just ignored what the units are or not provided them all together. Okay, nonetheless, let's move on. A right endpoint approximation looks like the following. Now we build rectangles for every one of our intervals, very similar to what we had on the left, only we don't use this left endpoint here, right? We shift over and we use the right endpoint for our first interval. So instead of taking our first velocity measurement at time 0, for like a left endpoint does, we say, well, let's say that we use whatever our time was at our velocity was at time 5. At time 5, our velocity was 30. So that is our first estimate of the velocity. And then we go on down the line, 50, 62, 66, and we end up using the one we didn't use last time, and that's 70, our rightmost value, right? And that's the difference between the left endpoint and right endpoint approximation here. You'll skip the left endpoint or the right endpoint, depending on whether or not you're doing a right or left endpoint approximation, respectively. So this is the same thing, delta t times all of the velocities added together, and a time, delta t is measured in seconds, right? It's a unit of time, times a velocity is a distance. So that's why this distance makes sense as an approximation. When we add all of that up, we get 1,732.5. Notice that the right endpoint distance approximation is greater than the left endpoint distance approximation. That matches our intuition with the graph because the right endpoint seems to overestimate our distance, whereas the left endpoint seems to underestimate the distance because the area under the curve is underestimated here, whereas in the right endpoint, it's overestimated. So there we go. Again, like I said, you might have to deal with this being in miles per hour and this being in seconds. The only thing you really have to do is realize at the end here that this is a unit in seconds, this is a unit in miles per hour, and you should probably convert one or the other. Probably it's easier to convert 5 seconds to whatever that is in hours, right? And that'll be 5 divided by, I think, 3,600. And that will be the number you multiply by 276. And that will give you something in terms of miles. Again, though, maybe we just assume that this is feet per second and these are seconds. And so our answer comes out as feet. It just simplifies it. Okay, so that's our introduction to areas and distances. What we'll do moving forward from here is we'll probably look at another problem or two where we find the exact area underneath a curve between two endpoints using a technique like this with a formula, with a trick formula like that. There are 2 more of those around. But ultimately, what we'll see is in the fundamental theorem of calculus, we'll see a nice connection between the antiderivative and the integral, and we'll be able to calculate these areas a lot more easily than with all the tools that we used previously.